Hello, welcome to Sergio Prado's YouTube channel. So in this video, we're going to talk about Linux core dump analysis. So we're going to learn how to do core dump analysis on a Linux system. So I have this very popular training called Linux debugging, where I teach several different techniques on how to debug an embedded Linux system. And one of the techniques that I teach is doing core dump analysis. So in this video, we're going to talk about what a core dump is, how we can generate a core dump, and how we can do the analysis, the requirements, the tooling, and everything. So yeah, let's get started. So I have here with me Big O Play, running a small embedded Linux system that I created with Buildroot, and that I have a few applications that that have some problem, and we're gonna here in this video do two core dump analysis. So let's start with the first one. Let me open here my terminal. So this is the terminal. Let me log in, and then there is one application here that is crashing, fping, as you can see. So I try to run fping, and I get this segmentation fault message. So what happened here is that the application tried to access an invalid memory region, and then the kernel captured that error because of the MMU, and then the kernel sent a signal to the application, call it sig-segv, and then the application just crashed. Brutally finalized its execution with this segmentation fault. So here we could use different techniques to try to find out the issue, right? So for example, we could start a remote debugging session with GDB. That would be one way to try to solve this issue. Another way is to generate a core dump. So what is a core dump? A core dump is a snapshot of the memory of the process that crashed or abruptly ended its execution. I have this article on my blog in case you want to read later, where I talk a little bit about this. So it's a kind of a written version of this video. And here I explain a little bit about what a core dump is and when it is generated. So you can see here that a core dump is generated if a process receives one of those 5 signals. So in this specific issue here, the process received this sig-segv signal. But other signals might create a core dump. So sigkit, that's when you send the kit signal to the process. You can do this, for example, by pressing Ctrl \. Sig-u, it's when the process, for example, executes an invalid instruction. Sig-abort, it's when the process call the system call abort. So if you write a program and call this system call, core dump might be generated. sigfp, it's when a program executes some kind of invalid mathematical operation. For example, on some architectures, you cannot divide by 0. If you try to divide by 0, you're gonna abort the execution with this signal. So again, if a process receives one of those signals, it will finish its execution abruptly. And a core dump might be generated in that case. Now, if we get back here to the terminal, we can see that no core dump was generated. Like we have no messages here about core dumps, and that's because there are a few requirements for a core dump to be generated. What are those requirements? First, the process needs like privileges to generate the file. So, for example, if I run a program here and the program crashes, then the program needs privileges in the directory that it is running to create a core dump that are actually this is configurable because the location of the core dump is configurable. So the process need privileges to write to the location of the core dump. That's one thing. Another thing is you need space in the file system because again, a core dump is a file that is a snapshot of the memory when the process crashed, for example. And of course, you need space, enough space in the file system to save this file. Another requirement for a core dump to be generated is a configuration per process. So every process on Linux has this configuration where you say the maximum size of the core dump of that specific process. And by default, it is 0 because actually this is inherited by the parent process that created the child process. And by default, it's 0. So every time you run a process on Linux, if the parent is configured with 0, then the child will also be 0. And that's the default configuration here. So there is one command that you can use, call it ulimit, to change this configuration. So with ulimit, you can change the limits of a process, and one of those limits is the core dump that you can change with this -c flag. And here you can define a size for the core dump, or you can just say unlimited. Then here you are saying that the size of core dump is unlimited. So what I have done here is I configured the shell program, that's Ash from BusyBox that I'm using here, to have an unlimited core dump. And all of the commands that are running here right now, in this moment, like it's going to be a child of this shell. That means it's going to be inherit this configuration. That means it will generate a core dump if it crashes. So now if I run fping, I should have a core dump. As you can see, core dumped. So now I have a core dump of this process. This is this file here, core. So this is the snapshot of the memory of that process that crashed. It's an ELF file, as you can see. So you can analyze this ELF file with any tools from your toolchain that is able to analyze ELF files. One of them is GDB. So we're going to use GDB to analyze this core dump in a few minutes. I just want to comment a few more things on this core dump file. So there is a nice documentation that you can read in the core man page. So if you run man5 core, you're going to have access to the man page of this core dump file, and then there are lots of documentation there about how a core dump is generated. You might want to read that. So here they talk about the requirements for a core dump to be generated. I mentioned a few of them, right? The naming of the core dump file, because this is configurable. As you can see here, in my specific case, it generated a file called core inside the root. That's because I configured that way. There is a file in /proc/c/kernel called core pattern. So there you can configure the name of the core file. And you can see here, I just configured a file called core with full path /core. But you can change, of course. You can, for example, add to the name of the file the PID of the process, the process ID, the timestamp of the moment that the process created the core dump. And I mean, you can do lots of different things with the name of the core dump file. You can also pipe to another process. That's usually what distributions do. So you can pipe, I think here we have an example, maybe pipe to system D. Here we go. So here we have an example where the core pattern is configured to pipe the core file to systemd core dump. And if you look at the configuration for Ubuntu, here I'm running Ubuntu 22.04, and we can check here the Ubuntu configuration. You're gonna see that it sends to another process called apport. That's a kind of a crash analysis tool from Ubuntu. You might even have seen like messages from apport and apport Ubuntu. So messages like crash report, the application has closed unexpectedly. So this is because the process crashed. It generated a core dump, and then that was sent to a port that show that message to you. It's really up to you the way you want to handle this, right? You need to be aware that if you leave that enabled by default, especially on an embedded Linux system, you might have problems because let's say you have an application that is constantly crashing, and you might just end up filling your file system with crash reports, with core dump files, and then you might end up with no space in your file system. The other issue is that usually we run embedded Linux on a flash-based device, and that means every time you create a core dump, you will write to the flash, right? And that might not be good as well. So be careful when using this feature on an embedded Linux system. Use with care, right? It's a useful feature, especially for debugging, but use it with. All right, now let's talk about how to analyze this file. Let's try to understand how we can analyze a core dump file. So I have the core file here. And what do you need to analyze the core dump file? You need a few things. So you need the GDB from your cross-compiling tool. So mine is this one. This is the GDB from my cross-compiling toolchain. You need the source code of the application that is crashing. So the source code of my application is here. So I'm using here build root to build the system. And in output fping, build fping, I have the source code of the application here. And I also need the binary that of the application that is crashing with debugging symbols. So I also have this here inside the source code. I have the application compiled in this src fping directory. So this is the application. I can confirm that it has debugging symbols here. So those are the three things that I need. GDB from my cross-compiler toolchain, the source code of the application, and the binary with debugging symbols. Now, here I'm using build root. If you are using Yocto, you're going to find those informations in a different place, right? You might need to create an SDK with Yocto. I will point to you a few resources later if you work with Yocto and want to do the same thing. All right, now let's analyze this core dump. So the first thing I need to do is to get the core file, right? For that, I'm going to use scp because I'm running ssh in the device. So I'm going to copy root core here. copy. Now I have the core file here on my machine. Now I can just start it with GDB. So I start here the GDB from my toolchain. And then I have to pass the binary with debugging symbols, -c, and the core file. That's it. Now, I might also want the graphical interface from GDB, what we call it tree mode. So, like this. Let me do a thing here, so let me change this. All right, now it's better. Because I want to increase the size of the font here for you. So this is the complete command. Arch, so the GDB, the binary with debugging symbols, the core, and tree mode. Here we go. Now, let me decrease a little bit the size of the font. A little bit more. No, I think it's good. So, I opened the core file, and what I have here? I have here the location of the instruction that caused the crash. And GDB is able to convert that to a line of code. So let me show you here. So here we have the search code, optiparse.c, line 217. And here we have the line. So this was the line that caused the crash. So just by opening the core file, we can see the line that caused the crash. And here we not only have the location of the crash, we also have access to the memory. So I can inspect the memory here. I can print, for example, if we look at that line that crashed, what could be the reason that caused that crash? We have there 2 pointers, right, that are being referenced. We have the options pointer and the argv pointer. So one of them is invalid. I can print the options pointer. It seems to have some address, right? I can try to reference that if I print with asterisk. I can dereference that pointer, it seems, right? Because I can see the contents of that struct. So it doesn't seem to be the issue here. Now, we have also this argv pointer. And if we look at the structure, we will see that the argv pointer is null. And that's our issue, right? We can print here options argv. We can see that argv is 0. So that's the reason of the crash. Now we might try to analyze this. Why argv is 0? If we look at the function, we're going to see that this options struct is passed as parameter. We need to go to the color of this function. And since we have this snapshot of the memory, we can do a backtrace. So bt backtrace, we can see the function that called optiparse long, and we can see that it was main, and main is in frame 1. So I can go to frame 1 now, F1, and this was the line that called function that crashed. Now I can look at this struct, optiparse state. This struct has the argv null. So now we might want to look at the code to see where this struct is initialized. So I can go up a little bit. optparse state. And then we can see that here in line, let me show to you again. I need to, so let me show to you again here, optparse init. This is the line that it is, this is the function that it is initializing this structure. You might want to have a look at why, right, the argv parameter inside this function is null. So what we can do, of course, we could go to the source code, but let's try to avoid that. Here we can use this list command from GDB to list the function optparse init. We can see that this function optparse init receives the optparse struct and also the argv. And then this second parameter is initialized in the argv element inside of the struct. And again, if we look at the call, we're going to see that it is null, right? So this is the issue. Instead of passing argv here, we are passing null. And then null is getting to argv inside that struct, and then later the application crashes because of this. So it was just an example, right? The important thing here is it's very easy, like to identify the line of code that caused the crash with the core dump analysis. And since you have the snapshot of the memory, you can inspect the memory. Of course, you cannot run the code step by step, but you can inspect the memory. You can try to understand what happened with that code. That's why we usually call it a post-mortem analysis, right? It's like an autopsy, like the problem already happened, right? Someone is dead. Now you're trying to identify why it is dead. And you can inspect. And you have that snapshot of the moment that the crash happened. So it's a very interesting technique, right, to analyze problems on Linux. Before we finish this video, I want to show you another example. This one is very quick. So you can also analyze, like use a core dump to analyze when the software hangs. Let me show you. So I have this other application called HA2, and it should display information about network interface, but it is just hanging. It is not returning. We could debug this with GDB again if we want, but we can also debug this with core dump analysis. So how can we, since the software is not crashing, how can we generate a core dump of the software? That means take a snapshot of the memory of this program in execution. We can send to this program the SIGKIT signal. So for that, we can type control \. So control \/ will send the SIGKIT signal to the process, and now we have a core dump. And we can analyze. So this is the snapshot of the memory of that process. So let's do this. So now let me see what I am. Again, what we need to do this core dump analysis: the toolchain, the source code, and the application with debugging symbols. The toolchain we have, the source code is here, output build HH2, and the application with debugging symbol is here in this directory. So I just have to copy the core file, copy, and open with GDB. GDB h2-c core, and let's start the tree mode as well. Here we go. What we have here? We have the line of code that remember the software here didn't crash, it was hanging somewhere. So when I sent the SIGKit signal, it took this snapshot in the core dump snapshot, and here it is saying to me that in this snapshot the code was at this line 519 at h82.c, and this is the line. We can see here a while one. That's where the software was hanging. Of course, I added this line to hang the software. So we could very quickly identify where the software was hanging by just analyzing its core dump file. All right. So core dump analysis is just one technique, right, to debug Linux system being embedded or not. There are other techniques like tracing, debugging with GDB, and so on. I plan in the near future to show you how you can do the same thing with the kernel. It's possible to create a core dump of the Linux kernel, but it's kind of more challenging because you need to boot a new kernel to create a core dump of another kernel. So there is a system call in Linux called kexec and a few tools to do this. So I plan to do a video in the near future about this. It's very interesting. So yeah, I hope it was useful for you, this video. I hope you enjoy it. I'll leave some links in the description of the video. Don't forget to like the video and subscribe to the channel if you are enjoying the content. Also leave your questions if you have any about this topic in the comments of the video. And yeah, hope you enjoy it. Next time, bye bye.